So we have now seen how the ABC Preon model dovetails nicely into the power of the Standard Model, and we have seen how it is simpler in its underlying description of nature. We have also seen how predictions for new physics have been made, and how some of these predictions can even be quantitatively defined, such as the prediction for a 69.6 GeV Z-like peak in lepton and hadron colliders. But at this time, it is relevant to look at some of the opportunities present for improvement. Firstly, it must be admitted that as of now, the ABC Preon model has very limited calculational abilities. Ideally, there should be some underlying theory that can be used to derive the masses of the various composite particles that are known to exist. Note that the Standard Model also has difficulties in this regard, but that the Standard Model is further along with its theory of quantum chromodynamics than any theory is for the ABC Preon model. Also, there may be some exotic results that are present in the Standard Model that are not nicely explained by the ABC Preon model as of now. But an important point is that the ABC Preon model is a model that has been pursued by a single individual for about 5 years, whereas the Standard Model has been pursued by thousands of physicists for decades. Hence, it of course stands to reason that the ABC Preon model is in its beginning state and opportunities exist for improvement. My request of the high-energy physics community is that they not look for the first possible reason to reject the theory and then consign it to the heap of nutty ideas, but rather that the high-energy physics community point out reasons for rejection and then work to understand how to overcome these problems. Keep in mind that the Standard Model grew in just that way. The difference, of course, is that the Standard Model was largely the only game in town, and so when problems arose, it was viewed as a great achievement to overcome the problem. The problem was not used to condemn the entire theory. As one example of this approach, look at the top quark analysis above. At first I believed that since no quark could be found at such a high mass, this was a severe indictment against the ABC Preon model. But upon further reflection, I understood how the signature naturally came about. I suspect that similar progress can be made whenever new problems arise. Of course, it may be that the salvation of the model requires that some new particle be proposed at some point, and while that would be regrettable, it would not be surprising. Note that every theory of matter has suffered from just that problem in the past. But such a fate does not mean that we should abandon the theory completely, as it can still be very useful. For instance, one need look no further than the Standard Model itself to see how a useful model can grow over time. Next, I'd like to say a few words about the present competition to the ABC Preon model. Preon models have been around since at least 1974, which is the date of publication of a paper by Paty and Salam that proposed a substructure to quarks and leptons. A book on Preon theories was published in 1992 by D'Souza and Kelman, and I would refer you to that book as a good place to read about Preon history. There are, of course, many theories of elementary particles that have been put forth by individuals over the past several decades. It really is quite a cottage industry. As a reviewer for physics essays, I have seen many such efforts. The vast majority are dismissed as the works of cranks and crackpots, and for the vast majority, this is a fair judgment. Most of these works have a common theme. They generally start out with some ill-defined concept that the author feels is quite profound, but that readers can typically not understand at all. The ill-defined concept is then infinitely malleable, so that in each and every case, an exact calculation of every mass of all known particles can be obtained to the limit available on the author's calculator. Almost without exception, these efforts to explain nature yield no new predictions for results not yet known, and the author will even claim to be able to explain anything once it has occurred. It is this large amount of crackpot effort that makes it very difficult to get any new serious idea heard, since scientists generally reject any new idea quickly once it sounds sufficiently different than the Standard Model. And yet the primary competition to any Preon model is the Standard Model itself, which in fact suffers from many of the same flaws as do the crackpot efforts. The Standard Model has a very large number of arbitrary inputs and has been modified over time every time a new result occurred that was outside of its original bounds. But while the Standard Model does commit the same sins as the crackpot efforts, there is a large difference in scope. The Standard Model has been modified relatively rarely and does not need a modification for each and every new experimental result. And the Standard Model has predicted some phenomenon before they were discovered. So while the Standard Model is admittedly flawed, any true judgment must be that it is far superior to the vast majority of its competition. This webinar has presented an overview of the ABC Preon model. While it is in its early stages of development, and while it has some opportunities for improvement, there are many philosophical advantages to the ABC Preon model that will now be emphasized over several slides. The first advantage is that it dovetails nicely into the Standard Model as a means to explain the various particles and forces known to exist. The ABC Preon model is, after all, a Preon model. This means that it proposes the existence of a smaller number of new particles that can be used to construct the known existing ones. Quarks are understood to be bound quantum states of a C preon bound to either an A or a B preon, while leptons are understood to be a quantum state of an A antipreon bound with a B preon. Hence, all of the Standard Model success can be incorporated into the ABC Preon model. Leptons still exist, and quarks can still be used as handy names for the categorization of the more complicated hadrons. A second advantage of the ABC Preon model is simplicity, as the 36 quarks and 12 leptons of the Standard Model have been replaced by the 6 ABC Preon particles and their antiparticles. Historically, the finding of such simplicity generally leads to an advancement in our knowledge about the universe. The next significant philosophical advance of the ABC Preon model is that it reduces the number of forces understood to exist in nature. Gravity and electromagnetism remain unchanged as one goes from the Standard Model to the superior understanding of the ABC Preon model. A force proposed to be carried by the neutrino is postulated to be the strong force that binds preons into leptons and also binds preons into hadrons. But the weak force has been identified not as a force, but rather as another of nature's examples of quantum tunneling. In addition to the advantage of reducing the number of forces, this is further advantageous in that it restores the attribute of direction to all known forces. In the Standard Model, the weak force does not have a direction while the other forces do. In the ABC Preon model, all forces have direction. Lastly, note that the low-energy weak interactions are governed by an interaction mediated by the masses of the weak bosons in the standard theory. Here, those mass relations are again seen to come into play during the quantum tunneling of the preons. Hence, the ABC Preon model has used quantum tunneling of the preons to replace one of the known forces of nature. The ABC Preon model also allows for an entire quantum number, color, to be set aside. Of course, the new neutrinic charge has been added to the discussion, but by eliminating color, one can also eliminate the 8 gluons from the mix of elementary particles. A further advantage of the ABC Preon model is that hadronic matter and leptonic matter are each now seen to be made up of the same preon material, rather than having a disjoint set of constituents, as is the case for the Standard Model's description of how particles are constructed. Importantly, the ABC Preon model leads to a clear understanding as to why nature has several generations of particles that are otherwise identical. We have seen that the massive leptons are each various excited states of the same basic bound preon structure, while the various quark flavors are simply various excited states of the basic bound preon structures there as well. A further philosophical advantage of the ABC Preon model is that there is a symmetry between atomic physics and nuclear physics. Atomic physics is understood to be the physics of fermions bound by a force carried by a boson, while the ABC Preon model allows us to understand nuclear physics as the physics of what are possibly bosons being bound by a force carried by a fermion. Another advantage of the ABC Preon model is that there is a clear dichotomy between charged matter, which has mass, and force carriers, which are massless. Lastly, it is important to note that the elementary particles predicted by the ABC Preon model can, in principle, be isolated, whereas the quarks of the Standard Model cannot be. Philosophically, the isolation of an entity will prove its existence far better than a situation where the entity itself must continually be buried within other particles. In fact, when looked at through the ABC Preon model, we can see that the A and B particles have already been isolated, as that is what happened when the W particle was discovered.